Welcome, physical science students, to our video about lenses. In the last video, we learned that mirrors form images by reflecting light rays. Well, lenses form images by refracting light rays. And we're going to look at different kinds of lenses, convex lenses, concave lenses, and then we're going to look at how eyesight is affected by lenses. So first of all, what is a lens? It's just a transparent material with at least one curved surface that causes light rays to refract. Remember, that's the bending of light as it travels from one medium to another. And as the rays pass through, they are going to refract or bend because they travel at different speeds in the air as opposed to in whatever the lens is made out of. So a convex lens would be right here, and it is convex on both sides in this case. It can be flat on one side. But here we have a convex lens that is thicker in the middle than at the edges. A concave lens would be thinner in the middle and thicker at the edges. So let's take a look at a convex lens. All the light rays traveling parallel to the optical axis in this figure are refracted so that they pass through a single point. And when they pass through that single point, we call that point the focal point. The focal length right here of this lens will depend on the shape of the lens. If the sides of a convex lens are less curved, the light rays will bend less. Also, lenses with flatter sides have longer focal lengths. Also, you can see that light rays traveling right along the optical axis are not bent at all. So let's take a look at the different images formed by a convex lens. And this is similar to the images formed by our concave mirror because there are quite a few different situations that can happen with a convex lens. First, let's look at a distant object. Distant meaning it is beyond 2 times the focal length away from that lens. Its image is going to be real, even though it's on the other side of the lens, because light will actually travel through and through the lens and hit that image. The light is forming that image. It's not virtual rays, but they are real light rays, and the image will be inverted and also diminished and smaller. If we place an object right at 2 times the focal length, the image will be the same size, but it will also be real and inverted. If we place the object between the focal length and 2 times the focal length, our image is going to be real and inverted, but it will be larger than the object, and it will also be beyond 2 times the focal length on the other side of the lens. You can see that these are getting a little bit farther away as the objects are getting closer to the lens. If we have an object right on the focal point, there will be no image, and refracted rays will all be parallel. If we place the object in between the focal length and the lens, we're going to get a virtual image, and it's going to be upright, larger than the object, and it's going to be behind the object on the same side of the lens. Now let's take a look at the refraction of light through a concave lens. Here is our concave lens, and you can see that the light rays will hit that concave lens and light will be refracted out. The light does not converge to a focal point in this case. In this case, the focal point is actually on the same side of the lens as the incoming light rays. And so images are always virtual for a concave lens. They're virtual and they're going to always be on the same side as the object, and they will always be upright and smaller than the object. So here, take a moment and see if you can do a quick review with yourself of the different kinds of images formed. Are they virtual? Are they real? Are they inverted or upright? And what is the size compared to the object? Here are the answers to reviewing the images formed by the 2 different kinds of lenses, convex and concave. Make sure you got all those right and you understand the different types of images formed. So what determines how well you can see this object in front of you now? Well, if you do not need corrective lenses, the structure of your own eye gives you the ability to focus on this image and on other objects around you and see them clearly. How does this work? Well, light enters the eye and passes through a transparent covering on your eyeball called the cornea. And the cornea causes light rays to bend so that they converge. After passing through the cornea, the light passes through the opening called the pupil right here. And then the eye lens right here is a flexible convex lens. And it helps focus the light rays so that a sharp image is formed back here on the retina. And remember, the retina is that inner lining of your eye, which has cells that convert the light image into electrical signals, which are carried along your optic nerve to your brain, where they're interpreted. So how are your eyes able to focus on close-up objects like your iPhone, as well as objects that are farther away, like your friend across the room from you? Well, you know that to see an object clearly, that image must be focused sharply on your retina. And the distance from your retina to your lens is always the same. Well, fortunately, the lens in your eye is flexible, and the muscles attached to it change the shape of that lens, and therefore change its focal length. Remember, the location of an image is formed by a convex lens, depends on the focal length of the lens and the location of the object. So by changing the focal length, by changing the shape of the lens and then therefore the focal length, the eye can focus on distant objects as well as close-up objects. You can see that there is the lens is less convex here to focus on distant objects, and the lens is pushed into a more convex shape to focus on the close-up objects. So let's take a look at a few vision problems. Astigmatism would be one. Astigmatism occurs when the surface of the cornea is unevenly curved, and it causes blurry vision at all distances, and corrective lenses also have uneven curvature to compensate for that problem. Now we have farsightedness and nearsightedness. Farsightedness is when a person can see distant objects clearly but not close-up objects. Nearsightedness is when a person can see nearby objects very clearly, but they cannot see distant objects clearly. Now, how do corrective lenses help compensate for farsightedness and nearsightedness? So here are some corrective lenses for nearsightedness and farsightedness. Remember, a nearsighted individual is unable to get a clear image for distant objects. So if we think about distant objects way off here, the rays are nearly parallel coming into the eye, and in a nearsighted person, the light rays from these distant objects converge too much, and they form a sharpened image that's in front of the retina. And so the retina perceives a blurry image. And this could be corrected by putting a concave lens in front of the eye, and that makes the light rays spread out before entering the eye, enabling a sharp image to be formed on the retina. Here is the corrective the corrective lens for a farsighted person. You can see that a farsighted person has an image, the focal point ends up being behind the retina, so we get a blurry image on the retina for nearby objects. If a convex lens is put in front of this person's eye lens, then a sharp image can form on the retina. Advanced ideas, converging versus diverging lenses. Where did those words come from? Research a very, very famous early physicist who was Arabian and was way ahead of his time and made tremendous advances in optics. Look at the manufacturing of convex and concave lenses, or look at the invention of spectacles. That's a good one too, or other ideas that you might have, and look into those, do some research, come up with what you have to show me, and I look forward to seeing you in class.